Today we'd like to talk about VEMPs, vestibular evoked myogenic potentials, and in particular using the Interacoustics Eclipse advanced two-channel auditory evoked potential system in order to acquire C-VEMPs and O-VEMPs. This is the anatomy that we're dealing with, and one of the things that makes this an extremely compelling test for audiology clinics that are doing vestibular testing is that when you add VEMP testing to the VNG testing that you're already doing on vestibular patients, it increases the sensitivity tremendously. And if you were to even add VHIT, video head impulse test, to that, then you would have a very, very, very comprehensive test set, because you would be able to test all 6 semicircular canals as well as all of the other anatomy involved in the vestibular system. Your sensitivity would go sky high. Sensitivity is what's all important in vestibular testing. I've been involved in it since the 1970s, and the problem that we had is the sensitivity was very low. All we did is an ENG test, and a lot of times doctors would refer patients that had legitimate symptoms, sometimes acute symptoms, and it would come back with no findings, simply because the test wasn't sensitive enough. We weren't able to test every component of the vestibular system. But now we are. So that has changed. And it has taken from the 1970s until now for this to develop. So VEMP, vestibular evoked myogenic potential, is what we're talking about today, and this is the anatomy involved. When we are doing, there's 2 types of tests involved. There's a C-VEMP, or cervical VEMP, and an O-VEMP, or ocular VEMP. The cervical VEMP is going to involve the saccula, and the inferior vestibular nerve. And the O-VEMP, the ocular VEMP, is going to involve the utricle and the superior vestibular nerve. So that's important to know. It's like this: C-VEMP, cervical VEMP, the saccule and the inferior vestibular nerve, and it's also connected, as you can see in the anatomy, it's connected to the posterior canal. So this would be very interesting for people doing physical therapy, because this would be involved in their linear movements and assist them with up and down movements. So physical therapists would be very interested in this when it comes to therapy. O-VEMPs, on the other hand, the response originates not from the saccule, but from the utricle, and it's mediated by the superior nerve rather than the inferior vestibular nerve. And the connection is with the horizontal canal, okay? And so something that's going to be important here is horizontal movements of the patient and assisting them with forward and backward motions for physical therapy. So all that taken into account, these 2 tests are important. Not C-VEMPs only or O-VEMPs only, but both together, along with, it doesn't make the other tests obsolete. It would be used along with VNG and hopefully VHIT, video head impulse test, as well. So let's talk about the C-VEMP first. C-VEMPs are short duration. It takes place in less than 100 milliseconds. And it's electromyogram, or an EMG. They're evoked by high-level acoustic stimuli and recorded by surface electrodes over the contracted sternocleidomastoid muscle. And this is what the response looks like. It's a very easy response to get. You get it within just a number of seconds. Just 100 or even less stimuli. We call it a sonomotor response, And there is a receptor, there's an end organ, right? There is an afferent pathway an efferent pathway, central connections in between them, and end muscles, right? So it's a complete system. And one thing that's good news about this test is that it is not correlated with sensorineural hearing loss. Sensorineural hearing loss prevents you from doing other tests, makes them contraindicated. But it's not the case in this. Since it has nothing to do with that, patients with significant sensorineural hearing loss, even deaf patients can be tested. The thing that would affect it is a conductive hearing loss. In fact, a conductive hearing loss would make the test contraindicated. Here's another key concept. We are really using high pressure sound stimulus as a way of kind of punching the saccule. Punching the saccule. So we're using it in that means. The frequency of it is going to be important to us, but also the intensity. So this is going to be a high intensity stimulus, very short duration stimuli, and over a short period of time, less than 100 milliseconds. Here's a key concept. The CVEMP is a stimulus-related attenuation of the EMG activity in that sternocleidomastoid muscle. So it's an inhibitory response, not an excitatory response. It's inhibitory. That's a key feature of this test. Different than the other tests that we're used to doing in audiology, the other electrophys tests. So the patient will have to contract their sternocleidomastoid muscle. And when we do the test, we'll show you exactly how they're going to do that. And if there is no EMG activity, in other words, if that muscle isn't contracted, then this response will be absent. The presence of an acceptably high activity or contraction of the sternocleidomastoid muscle and an absent CVEMP suggests an impairment, of course, in the affected ipsilateral, saccule, and/or inferior vestibular nerve. So here's the electrode montage that we were using for the first couple of years that we were doing VEMPs. And eventually we changed that because a couple of studies indicated that another montage would be better. So right now, we put the active electrode, right? Instead of on the top of the sternum, which you could put it, right? It'd be so much easier to put it on the high forehead. So we're putting on the high forehead now, just for the sake of convenience. The reference electrode is the ipsilateral sternocleidomastoid muscle. And we'll show you exactly when we do this. And of course, the ground you can put on the low forehead. And so that montage works fine. You've got a reference electrode on each of the sternocleidomastoid muscles, and you have an electrode on the high forehead and the ground on the low forehead. Works perfectly. And the position of the patient is important, as you'll see when we actually do the test, but we have them lying supine. And when we start the stimulus, we tell them to raise their head like this, 3-4 inches, so that they can see their feet from toe to heel, and then to turn away from the stimulus, all the way 90 degrees. I tell the patient to try to touch his chin to his shoulder. This gives you a maximal contraction of the sternocleidomastoid muscle and the best response. There is an option on the interacoustic system. It's one of the only evoked potential systems that has this option, and it's an option for an EMG monitor so that the clinician can see and the patient can see how strong a contraction they are making, and they can exert as much contraction as necessary to bring the meter into the green area the correct area. And they can make sure that that contraction is the same for right and left, because that's going to be important, because that's the big indicator, a difference between right and left. So we got to make sure we get the same muscle contraction on both sides. Anyway, our results will look like this. This is a C-VEMP response, left and right. It's a normal one. It's one that I did on myself. That's what they'll look like. And the VEMP response is normal when the asymmetry ratio of the right versus the left amplitude, right, when that asymmetry ratio exceeds 0.35. An asymmetry ratio is simple. It's the difference over the sum, right? So if we go back and look at the response here, we're looking at the amplitude of the response. We have P1 and N1. It's a typical way to mark it. And we're measuring that amplitude, and we're looking at that on the right versus on the left. And then calculating the asymmetry difference. And when that asymmetry difference exceeds 0.35, that's when it's a positive finding. On the Interacoustics Eclipse, if you have the VEMP option, it certainly does the calculation for you. So you don't have to calculate manually the asymmetry difference. It will do it for you. In this one that I did on myself, right and left here, the amplitude, this is the peak to trough amplitude of the C-VEMP response on the left side was 87 microvolts. 87 microvolts. On the right side, it was 59 microvolts. And when you do the difference over the sum and calculate it, it comes out to 0.19. See, this equipment does that automatically for you. And of course, 0.19 is normal. This is the protocol that we use. The stimulus we use is a tone burst. Actually, a 500 hertz tone burst. The polarity that I use is condensation. Remember, I'm punching the saccule with it. And it is applied at a slow rep rate, somewhere between 5 and 8 stimuli per second. The intensity is the loudest intensity I can get out of whatever piece of equipment I'm using. And typically, I try to get 100 and even 105 dB NHL. The stimulus envelope is the typical stimulus envelope that you would find. In other words, 2 cycles of rise time, no plateau time, 0 plateau, and 2 cycles of fall time. And the gating on it can be linear. You can use Blackman if you want, but it could be linear also. Again, I'm just using this as a mechanical punch. The gain is much lower. This is a much larger response than we're used to getting when we do ABRs or ECOGs. So the gain, the actual gain of the equipment needs to be very, very low. Okay? Different equipment uses different ways to specify gain. We shut the artifact rejection off, and our filtering is only 10 hertz to about 750 hertz. The response window, the ideal response window is minus 20 milliseconds to about 80 milliseconds. And the number of stimuli is typically 120, or somewhere between 120 and 200 stimuli. And the scaling, of course, is turned down to the point where you can actually size the responses properly on the screen. Many times when you do this, it's completely off the screen while it's running, and then when the test finishes, I scale it way down so that it comes into the proper perspective. What are you going to get? You're going to get something like this. You're going to get a positive peak and a negative peak, and the positive peak will be somewhere between 12 and 19 milliseconds. The mean is 16.9, and you can see that If you went out 2 standard deviations, it would put you past 20 milliseconds. That's the positive peak. The negative peak is somewhere between 20 and 28 milliseconds. And you can see the mean and the standard deviation there. So what is important is not the latency. That's only important so that you know that you have actually a VEMP response. But what's going to be important is our amplitude and our asymmetry ratio between the amplitude of the response on the left versus the response on the right. The typical P1N1, that typical peak to trough amplitude, is going to be, the mean of this one study was 170 microvolts, 180 microvolts, but you see the standard deviation is 120 microvolts, standard deviation. So it varies quite a bit from one person to another. I had a class once at Auburn that I was doing in electrophys, and we were going to demonstrate to the students a cervical VEMP test. And I looked at the students, and I saw one student who was very muscular. And I asked them what they did, and they said they were in the ROTC. They got up early in the morning and did push-ups and everything else, ran 5 miles. I said, oh, you're going to be the subject. Because you could tell that they really had a well-defined sternocleidomastoid muscle. A lot of muscles in the neck. And so that was a tremendously big response. It was like 300 microvolts on both sides. And so that's why there's a lot of deviation between normal patients. Okay, so this next slide will be interesting, and the reason the monkey is scratching his head is because VEMPs can be abnormal in patients with the following pathology. And look, vestibular neuritis, acoustic neuroma, labyrinthitis, brainstem stroke, conductive hearing loss, of course. That's going to make it contraindicated. Meniere's disease, and superior canal dehiscence, in particular, superior canal dehiscence. And so this is another reason why you don't do any of these tests in isolation. In other words, do only a CVEMP, right? We need a CVEMP, an OVEMP, a VNG, of course. We need to know the patient's history, and a doctor needs to do a physical examination. All together, even with the audiology information, we can come to a conclusion. And this is what will happen. This is how these different pathologies will affect the VEMP test. You see, in Meniere's, depending on the stage that this condition is in, the response could be absent, present, or enhanced, right? It could be absent, reduced, or enhanced. So with Meniere's, it's a little confusing, but I'm going to show you something that can help pin it down. Superior canal dehiscence, the response, the CVEMP response, is actually enhanced. It's abnormally large on that side. And then in other pathologies, like labyrinthitis, vestibular neuritis, etc., the response is either absent or reduced significantly, so that the ratio, the asymmetry ratio, exceeds 0.35. In superior canal dehiscence, a lot of times it is a little confusing because you have one response that's extra large, it's enhanced, and on the other side it maybe seems normal. So is the other side weak? Is that my problem? Or is that enhanced side enhanced? Sometimes it's hard to tell. Of course, you do have the patient's symptoms, but one way to find out is to simply do a search for threshold. And typically, in a normal patient, the CVEMP response is present at high intensities. It's certainly present at 100, it's present at 95. When you get down to 90, you're about at threshold. Move down to 85 or 80, it's gone. Unless the superior canal dehiscence. You have an enhanced response. Also, when you do threshold, instead of the threshold being 85, 90, it certainly could be down there at 60, 65, right? A reduced threshold for the response. So that will help identify superior canal dehiscence. This is the defining test for superior canal dehiscence. And remember Meniere's? Well, there's a number of studies that show that there's a phenomenon that takes place in the VEMP test, the C-VEMP test. The C-VEMP response is normally the highest amplitude at 500 hertz. That's why we use a 500 hertz tone burst, right? But with Meniere's, it's shown to shift. It's like the fundamental frequency response shifts so that the peak response, the highest amplitude response, now occurs around 1,000 hertz instead of 500 hertz. So another indicator of Meniere's would be a shift in frequencies. So if you did the test at 500, 750, and 1,000, and you found that the highest amplitude was at 1,000 rather than 500, then that would be an indicator of Meniere's. Here's a case where we found that exact same thing out, you know. Typically, 500 gives you the highest amplitude C-VEMP response, and as you raise the frequencies, the response amplitude goes down, and you know, when you get past 1,000 hertz, you can't even get the response. However, in the case of Meniere's, you do it at 500, you do it at 750, and now the response has a higher amplitude at 750. Do it at 1,000, it has the highest amplitude, and it doesn't start to reduce until you get beyond 1,000. And there's still a response present at 1,500 even. So, remember I told you that an option on the Interacoustics Eclipse system is a EMG monitor. That's something that we always wanted because something that could cause us a false positive in a cervical VEMP is that the patient uses more effort or less effort as they're contracting the sternocleidomastoid on the right versus the left. But if we had a way of monitoring that, it would make it easier. Well, the Interacoustics Eclipse has a beautiful EMG monitor built into it. It is an option, but it's a relatively low-cost option. And this way you can see very easily on a bar graph how much contraction is in that muscle. It starts out red and then goes to green when it's between the lines, and that's where you want it to be. And you can urge the patient to produce that. And we could put a secondary or an external monitor in a location where the patient can see it, and they would be told to contract that muscle and use more and more force until it comes in the green, and then to do the same thing on the other side. This is how the monitor would look that the patient is looking at. And see, this will start out in red, and as they contract the muscle more, use more force, it goes into the green here. That's what they want. And there's also a meter, just easy ways for them to see what's happening and relate it to the contraction of the sternocleidomastoid muscle, or SCM it's called most of the time. Okay, so that's the cervical VEMP, the C-VEMP. Again, once you get used to doing this, it's very easy to do. You're talking about only 100 stimuli, so it's something that you could acquire within just a few seconds on right and left. So people who do it end up liking it because it's a quick and easy test. It could be contraindicated on some patients with conductive hearing loss, of course. That's preventing you from punching the saccule hard enough to get a response. And it might be contraindicated with people that have, like they're not able to do the task. I had them lying down flat and supine, and then raising their head 3 or 4 inches and then turning 90 degrees. If that's not possible, what I do is adjust the exam table into the caloric position. So now the back of the patient is raised up 30 degrees, and sometimes that makes it easier. If they can't do that, then it might be contraindicated. Okay, so let's talk about the ocular VEMP now, right? This is a little different, and I'll show you the electrode montage for it as well. It represents evoked extraocular muscle activity associated with the VOR, the vestibular ocular reflex. It doesn't represent the movement of the eyes. Even though we're putting an electrode under the eye, it doesn't represent the movement of the eye, right? It's just that the response is recorded on that muscle. And it is an excitatory response. Unlike the C-VEMP. The C-VEMP, as you heard, was inhibitory. This is an excitatory response, like all the other responses, ABR, ECOGs that we're used to doing. And the end organ is actually the utricle instead of the saccule. And the response is mediated by the superior vestibular nerve versus the inferior, and it's recorded on the oblique ocular muscle right here under the eye. And the same pathologies that affect the C-VEMP can also affect the O-VEMP. Right? It just depends on which anatomical structures are affected. And which pathology involving the associate anatomical structures, we're going to find this in the contralateral response. So that's another thing that's important about the O-VEMP. It is a contralateral response. The C-VEMP wasn't. It was an ipsilateral response. This is a contralateral response. So those are the differences. And this is the protocol that we use. We use as high as intensity air conduction as we can get, a 500 hertz tone, and depending on which piece of equipment you're using, it may be different. With the interacoustics, we typically use 97 dB NHL, but 500 hertz tone burst, and we're using a stimulus envelope of 222. So that's two cycle rise time, 2 cycle plateau time, 2 cycle fall time. At a pretty slow rate, we use 5.1, so it would be something like that. We do about 200 stimuli. And I'll show you our electrode montage pretty soon. And during this test, the patient is gazing upward. That's the only thing they have to do. They have to look upward, and at least 40 degrees. So sometimes it's good to put a center target and then one that's calculated up 40 degrees to be sure that they're raising their eye. And the only reason for that is to bring that oblique ocular muscle as close to the surface of the electrode as possible. And we're going to get a response that's around N1 is around 12.8 milliseconds plus or minus, and P1 around 15.9 milliseconds. The response, as I said, is from the contralateral eye, and of course what makes it abnormal is when the asymmetry ratio exceeds 0.35, just like it did in the C-VEMP. This is what the response is going to look like, and this response is way smaller than the C-VEMP response. It is very much like the amplitude of an ABR or an ECOG. It's more like that. So we're going to put the gain back up where it was for like we were doing ABRs and ECOGs. But you see, here's the calculation of this test that I did on myself, and you can see that my asymmetry ratio is only 0.08, so well within the normal range. Now my next slide is going to show you the best possible electrode montage. We've been working on this a long time, and we've tried everything. And there have been studies published using numerous different montages, including on the chin and on the nose and a number of different ways. But this is what makes all the difference. Notice I have the two reference electrodes underneath the patient's eyes, and we even cut the electrodes so that we can get them closer, because we want them as close in as possible. And we don't want them right at the bottom. We want it off to the side, halfway between the center point and the end point of the eye, halfway between there. You'll see that. We'll take a picture of me when we get the electrodes on too. And then the ground electrode is on the high forehead, and that active electrode, or the non-inverting electrode, is right there on the low forehead. Works perfectly. And there's even an alternative transducer that could be used. There's a study going on right now using bone instead of air conduction for an OVEMP. It has to be a particularly strong bone vibrator. In fact, it's a B81 to give you enough of an output for a 500 hertz tone burst. But 70 dB NHL is the intensity. The bone vibrator is located on the mastoid, and it gives you at least double the amplitude. At least initially, that's what the study is showing. The study is not complete yet, so we're not recommending that, but there's a high possibility that that would be the stimulator of choice for OVEMPs. What we're going to do now is we're going to use the Acoustics Eclipse equipment to actually do a CVEMP and an OVEMP, and you'll be able to see the test in action, electrode placement and everything else. This is the electrode montage for the CVEMP. Notice that I have the two reference electrodes, and sometimes they're called the inverting electrodes, sometimes they're just labeled minus versus positive. Anyway, they're on my sternocleidomastoid muscle. And you can see when I contract this by turning my head and trying to touch my shoulder with my chin as this muscle contracts, that it begins at the earlobe and goes all the way down to the clavicle here, right? And the ideal place on most people, you want the meatiest, biggest part of this muscle, but on most people, if you look at this, there's like an upper third, a middle third, and a lower third. Well, right smack in the middle of the upper third is usually the ideal place that is going to give you the most amplitude. It is also important not only that you get it right smack on the middle of the meatiest place on the SCM, but that you also are symmetrical from right to left. You don't have one down and one up or anything like this. So you're looking at the patient this way and make sure that everything is symmetrical, equal on each side. And then we have in this case it's the white electrode, but this would be the positive electrode or the non-inverting electrode, or sometimes called the active electrode, on the high forehead, and we have the ground on the low forehead. And that montage works perfectly. We're making sure that we got good impedance, like all electrophys testing. So we're doing two things. We're not just using alcohol wipes and degreasing the skin, but we are also abrading the skin. The abrasion is very, very important. And as you can see here, this is the impedance test on the Acoustics Eclipse, and there's a button right on the preamp, and you can push that, and you have an LED light for each electrode, each of the four of them. It's either red or green. Green means that it is at least as low or lower than the dial setting. So ideally, for all electrophys testing, we put the dial at 3, means 3K. So that means that the impedance is either 3K or less, and that would be recommended. If I were to go any higher, I'd go to 5, and some people even go to 10, but 3 is what's recommended. The better the impedance is, the better the response is, the better the signal-to-noise ratio is, the better the common mode rejection is, just better for everything. So that's something that we should be always concerned with. Anyway, so this is the correct montage for the CVEMP test. So here you see the patient lying supine, and when the stimulus starts, the patient raised their head. And it's best to have them be able to see their feet and then turn 90 degrees away from the stimulus, and I always say try to touch your chin to your shoulder. And as you can see, the response is acquiring on the right. Nice strong response. And the total test was just 100 stimuli, so it didn't take that long. It was just a few seconds. And we're going to do another one to see if it replicates, because if it doesn't replicate, you must investigate. There I am, up and over as soon as the stimulus starts, and we're merging the two so that they're superimposed to make sure that we have two good and equal replicable runs. And we do. So that's it for the left side. We've collected CVEMP responses on both sides, right and left. And we also did replications to make sure that we had a valid physiological response. And I like the replications to be similar to the original. So I'm moving this so that it's superimposed to make sure that that's similar. If I see a big difference, then I know there is a variance, there's some inconsistency in the patient's effort when he's contracting his sternocleidomastoid muscle. But that looks fine to me, so I'll just choose which one I want to use. Maybe I'll use this one, it's just a hair bigger. I could add them together and use the addition if I want. Some people do that. All right, so I'm going to use the bottom two. They replicated very nicely, and they look like great responses, and I'll mark them. Here's how I mark them. I'm going to go over and get P1, and I'm marking this left one here now because it's active. You double-click on the handle or the tag to make it active. And then I'll go over and get N1 and mark the trough. So it's the peak and trough, like that. I'll go over to the right response, double-click on the handle to make it active, go get P1, and mark the peak, get N1, and mark the trough. And now I can see, for the right side, for example, I can see my latencies. P1 occurred at 15 milliseconds, N1 occurred at 24 milliseconds, and my overall amplitude was 300 microvolts. Pretty nice big response. And if I want to look at all of that information on the other one, on my left one, that I'm double-clicking on that tag, and I can see my latencies. P1 is 15.6 milliseconds, N1 is 23.6 milliseconds, and the amplitude on the left side is a little bit higher even. It's 325 microvolts. Okay. Now, if I want to know my asymmetry ratio and have the equipment calculate that for me so I don't have to do the math, then I just make sure that they are married, and the way I marry them is make one active, go over to the other one that I want to marry to it, and just right-click on the handle and say Set as VEMP Partner, and then it will automatically calculate the asymmetry ratio, and in this case, here it is, 0.04. So, as you can remember, the abnormal is when you have an asymmetry ratio that exceeds 0.35, so this is well within the range of normal. One last thing you might want to consider, if there was a problem with the patient's effort in the CVEMP, where they may have used more effort when they were contracting the sternocleidomastoid muscle on one side versus the other, you can eliminate the effect by doing EMG scaling. And that's pretty easy to do. I can look and show my EMG graph here. And this shows if there is a difference in the effort. In this case, there wasn't much difference in the effort, but if there was, then I certainly can eliminate that difference by doing what we call EMG scaling. It takes that out. What we see is just a pure response. You're not connected to the amount of contraction. And so we made one of our two that are married together. Naturally, we have that active. We're going to right-click on the waveform of the other one, and we're going to say EMG scaling. We're going to turn the EMG scaling on. So this just applied the EMG scaling to this, eliminating the effect of the effort of the patient, one direction versus the other. And now we have a little bit of change. Not much change because my effort was very close to the same on both sides, but instead of having a 0.04 for an asymmetry ratio, now we have a 0.06. Makes no difference in this case, but it certainly could make a difference if the patient was maybe contracting their sternocleidomastoid muscle on one side in a way that was more powerful than the way that they did it on the other side and giving you a false asymmetry ratio. You can eliminate that prospect. Remember also that you have the EMG monitor drawing the contraction of the muscle, so you'll be able to know. You can see it and the patient can see it, and you'll another way of ensuring that the contraction is equal one side to the others. And in the Interacoustics Eclipse product, you don't have to put on extra electrodes for EMG monitor or anything like that. It uses the reference electrodes that are already on there. So now hopefully you know the anatomy involved, the pathology that could affect this response. You know how to collect the response, you know the electrode montage, you know the patient positions, all of these things that affect the response, and you know how to mark it and analyze it. So this is the electrode montage for the VEMP, the ocular VEMP. And there's a couple of things to note about this. First of all, notice the position of the two reference electrodes. Notice that the electrodes have been cut so that we could get the recording portion of the electrode as close to the eye as possible. And it's under the eyes, but it's not directly in the center. It is offset to the outside, halfway between center and the edge of the eye here. Okay? Why is that? Is because that position gives you the maximum amplitude. That's very important. Another thing that is important is this, remember, is a contralateral response, unlike the CVEMP. And so we have actually reversed the two reference or minus inverting electrodes. We've reversed them, left and right, because we want to actually measure a contralateral response. Okay? And my forehead's a little bit different too, because this time my active electrode, or my non-inverting electrode, my positive electrode, is on the low forehead, almost on the bridge of the nose, and the ground is on the high forehead. Just a little bit different electrode montage, but this is foolproof, and you end up with a perfect VEMP from it. Remember that the patient has to look up during this test, and their gaze upward would be continuous as long as the stimulus is present, and it would be at least 40 degrees from center. I make sure they're actually looking at the ceiling, and you can put a 40-degree target if you want as well. Okay, so now that you know that, we're going to actually do the recording. This is the setup for the left ear. Here we are with the VEMP test. As soon as the stimulus started, a patient was told to look up, and that should be at least 40 degrees. I like to put a center target for them to look up and then have them look and watch the ceiling the whole time. That's to move the oblique ocular muscle as close to the electrode as possible. And there you see the response on the right. It's just 200 stimuli. And so, again, it only takes a few seconds to do this. Then we always run a repeat. Here we are running the repeat. Patient is told to look up as soon as the stimulus starts and to hold their gaze on the ceiling, 40 degrees or more. And our second response is acquiring now. Again, just 200 stimuli, just a few seconds, and we like these to replicate. If there is a significant difference between the two, then I maybe do it a third time because maybe the patient did not keep their eyes elevated or something like that. But these replicated just fine, so we're going to accept both runs. Okay, so now we have recorded an VEMP response from left and right. In fact, we did a replication of each one, as you can see. And we always do a replication so that we're assured that we do have a valid physiological response. And I also like to see that there isn't much difference between the first one and the second one on the same side. This way, the patient, it ensures me that the patient used the same amount of effort. In the case of an VEMP, the only effort is looking up, but they certainly have to do that correctly and consistently during the test. And since there is no appreciable difference between these, I can select the two that I'd like. In this case, I'm going to use the lower two, and I can mark them. I'll do the right one first and double-click on the tag in order to make it active, and then select N1 and go ahead and mark it at the leading trough right there. And then I can go and select P1 and mark it at the peak right there. So I can see over here, I can see my latencies. N1 was at 13.6 milliseconds and P1 was at 19 milliseconds. That's within what I expect. So I have a good valid response. And it happens to be 3.2 microvolts. That's by amplitude. And that's about the amplitudes that you're used to measuring in ABRs and ECOGs. This is a lot lower amplitude than the VEMP, which is gigantic, so that's why we had to raise the gain when we did this test. So now we'll look at the left. I'll double-click on that tag in order to make it active, and I'll go get N1 and mark it in the leading trough, and then P1 and mark the peak. And once I do that, I can tell you some things, like I can tell you that N1 occurred at 12.6 milliseconds, P1 occurred at 17 milliseconds, I like that, and that the amplitude is a little bit larger than my right side, it's 4.28. So now I want to know what the asymmetry difference is. That's the big thing, asymmetry difference between these amplitudes left and right. So I have my left one active. I had double-clicked on the tag. So I'm going to now click on the tag of the right one and say Set as VEMP Partner. Once I do, then the software knows that these are the two that I want to use to calculate the asymmetry ratio, and it will do it for me. And it is 0.14. Well within normal, because you'll remember that an abnormal asymmetry ratio is something that exceeds 0.35. So I hope that that is helpful, and that that you have now an overview of these two tests and the anatomical structures involved and the type of pathology that can be that can cause this response to be abnormal.